This is a lecture on the topic Deaps. In this lecture, I'm going to cover the definition of a deap, insertion of an element into a deep, and deletion of the maximum element and minimum element from the deep. Okay, now coming to the definition of a deep. What is a deep? A deep is actually a complete binary tree, or some even call it an almost complete binary tree. Now I'll tell you why. See, this is the figure of a complete binary tree. It's called complete because all the nodes are filled. Now this is also a complete binary tree, or rather almost complete binary tree, because see, this is the last node and all the node before the last node is filled. And like suppose if this node is empty and this node is empty and there was a node over here and these two nodes were also present, then this would have been the last node. And this node before the last node is empty. So that condition would have been, that tree would have been not a complete binary tree. But in this case, yeah, this is a complete binary tree because this is the last node and all the node before the node is filled. Now coming to the definition of a deep. See, this is an example of a deep. For a complete binary tree to be a deep, it should satisfy certain conditions. So let us see. What is the first condition is that the root node should be empty. See, this is a root node and that is empty. So that condition is satisfied. And the second condition is that the left subtree should be a min heap and the right subtree should be a max heap. I hope you know what is a min heap and max heap. See, now here this is the left subtree and that is a min heap, as you can see, and this is a right subtree and that is a max heap. Now there is one, the other condition is the correspondence property condition. So that's nothing but, see, for every element in the left subtree there should be a corresponding element in the right subtree. Like for -1 it is 25, for 5 it is 15, for 3 it is 19, and for 8 it is 10. We have to see for left subtree, we have to see for the corresponding element in the right subtree. So for 8 it is 10, and for 11 there is no corresponding element over here. So in such cases, when the element is not directly present, what we do is that for finding the corresponding element of 11, we take the corresponding element of 11's parent, this element's parent, to be its corresponding element. See, now 5 is 11's parent and 5's corresponding element is 15. So 11's corresponding element will be 15. Similarly, 9 also does not have a corresponding element over here. So what we do is we consider its parent's corresponding element to be its corresponding element. So 9's parent is 3 and 3's corresponding element is 19. So 19 is 9's corresponding element, and similarly 13's corresponding element, which is not present over here. So 13's corresponding element will also be 19. See, now I can show you that. See, I have written it in this table over here. Now there is this is the formula for that, finding the corresponding element, about which I'll explain to you in the next slide. And this is I've reworded it in another, I've reworded the same thing. Like for every node x in the left subtree, there should be a corresponding node y in the right subtree. And if such a node y does not exist, like in this case, such a node y does not exist, then the node y of the parent node will be considered as the y node of such an element. Hope you guys understood that. And the last condition of a deep is that the element in the x node should be always less than or equal to the element in the corresponding y node. You can see it in the table over here. I've just listed all the x nodes and its corresponding x nodes, that is the y nodes. You can see that -1 is less than 25, 5 is less than 15, and so on. So while checking for the corresponding elements, you have to always make sure that the x node is always less than its corresponding element. If we say it in the other way, the corresponding element should be greater than its x node. So yeah, that's all about the definition of a deep. Okay, now I'll explain how to find corresponding element using that formula. So this is the same example, and here the height of this tree is 3. So this is the level 0, level 1, level 2 and level 3. And the numbering of the nodes is from left to right, and once all the elements in the particular level is finished, then it goes to the next level and the next level. So that's how it's done. The numbering of the node is done. So this is the first node, second node, third, fourth, fifth, sixth, 7th, 8th, 9th, 10th and 11th node. That's the last node. Now I've just added that corresponding element table over here. See, now, yeah, this is the formula for finding the corresponding element of a particular node. So see, -1's corresponding element is 25. So I've already shown it to you. So let's see it using the formula. -1 is in node 1 and 25 is in node 2. So node 1's corresponding element is in node 2. Now 5's corresponding element is 15. 5's corresponding element is 15 and 5 is in node 3. So its corresponding element is in node 5. So 3's corresponding element is in node 5. Similarly, 3's corresponding element is 19 and 3 is in node 4 and its corresponding element 19 is in node 6. So 4's corresponding element is in node 6. Now 8's corresponding element is what? 10. I've told you. And now 8 means the node 7. So node 7's corresponding element is in node 11. 7's corresponding element is in node 11. Now coming to 11. 11's corresponding element is 15. I've told you. So 11's corresponding element is 15. That is node 8's corresponding element is in node 5. Node 8's corresponding element is in node 5. Now 9. So 9's corresponding element is 19 and node 9's corresponding element is in node 6. So node 9's corresponding element is in node 6. Now node 10. So node 10's similarly node 10's corresponding element is also in node 6. So that is how we found it by seeing. So now I'll explain it to you using the formula. See, this is the formula where x represents the node, which node it is. And for elements we are finding corresponding element of the left subtree. So left subtree represents x and right subtree represents y. Okay. So when x value is 1, like we are finding the node of the first node, corresponding node of the first node, if an element exists at the index, that is the case which is that case 1, 3, 4 and 8, all these nodes have a corresponding element which actually exists. See, so that case we use this formula, and the case when otherwise means it does not have a node actually it does not have a corresponding y node, so we use this formula. That's the case for this 8th node, 9th node and 10th node. It does not have a corresponding node, so we use this formula. So now let us see. So for the first node, the formula is x plus 2 raised to L minus 1. So the L is the level. Okay. So first node 1 plus 2 raised to level is what? 1. So 1 minus 1. So that is 1 plus 1 will become 2. So the first node's corresponding element will be in position node 2. So yeah, that we got it correct, right? Now coming to the next one. Yeah, third node. Third node corresponding, we have to find the corresponding element. So third node plus, what do you have to do? For the third node, so the x value is 3 and 2 power, so the level, its third node is in level 2, so 2 minus 1, 3 plus 2 power 2 minus 1, x value is 3 and 2 power, the level is 2, so 3 plus 2 power 2 minus 1, so that will become 3 plus 4, that is 5. That is also, we got the correct answer. Now coming to the fourth node, so x value is 4 plus 2 power, that's also in the level 2, 2 power 2 minus 1, so 4 plus 2 6. Now coming to the 7th node, 7 plus what will it be? So that the level change, okay, it's coming to the other level. So 7 plus 2 power level 3. 3 minus 1. 3 minus 1. So it will be 7 plus 2 square, that will be 4. 7 plus 4 equal to 11. That also we got it correct. Now for the cases like otherwise, like actually there is not a y corresponding not present for that. So in such cases we use this formula. Now let us see for 8th node. So what is the formula? It should be x. If we are finding for x, the node means x by 2. This is a ceiling function minus 1 plus 2 power L minus 2. So for the 8th node, it will be ceiling function of 8 by 2 minus 1 plus 2 power 3. So the level is now 3. So 3 minus 2. So 8 by 2 ceiling function will get 4 minus 1 plus 2 power 3 minus 1. That is 2. So 4 minus 1 plus 2 will be 5. That also we got it correct. Now to the 9th node. See the 9th node, if you put in the formula 9 by 2 ceiling function minus 1 plus 2 again 2 raised to that's also in the level 3. So 2 raised to 3 minus 2, that's the formula. So that will be 5 minus 1 plus 2, that is again 6. And for the 10th node, it is again you put in the formula. So 10 by 2 ceiling function minus 1 plus 2 power 3 minus 2. So 5 minus 1 plus 2, that is equal to 6. So hope you understood that. So that is we can either use the formula to find the corresponding node, or we can actually directly find it. Okay, now coming to the creation of a deep or insertion of an element into a deep. So the creation of a deep is actually a step-by-step insertion of an element into a deep, because we insert or we create a deep by inserting each element into it. So yeah, when we want to add an element into a deep, we'll add it in the last node, or just after the last node, the last position we'll add a new element. So while adding such an element, there are certain things that we have to keep in mind. If we add an element over here, it can result in any of the following cases. First thing is that it may not violate any property. That means it is just perfectly fitting over here. So if we are adding some 12, so nothing is gonna, there is no property violation. It is satisfying max-heap property, correspondence property, mean-heap property, and all the properties it satisfies. So the second condition that can occur is a violation of correspondence property. Suppose we add 10. We are adding again 10 over here. So that will be a correspondence property violation, because 11's corresponding element will be that, right? So that it will change. So the 11's corresponding element will be that 10 that we have added, and 11 is less than or equal to 10. That is not the case, right? So that will be a correspondence property violation. And the next is correspondence property violation will also be there, and if such a violation is created and if we just swap it, then that may be result to a max-heap violation. So okay, for in this case it will be like correspondence property violation and then followed by a min-heap violation. That's because if we add some other element over here and if it's violating the min-heap property, and then just violation of the max-heap property and just violation of the min-heap property while we add. So I've just stated it over here. I'll just explain it to you with the an example so that it will be more clear to you. And one thing is that this similar to the min heap, the creation of an n element deep require order of n log n time. Just keep that in mind. Okay, now here is I've just taken the example. These elements are actually the elements in that figure, figure 1 that we have. So I've just rearranged it in a way, and it is a 11 element array. So we have to insert this into a deep. So let's see how it's done. So first what will happen is so we have anyway the root node should be empty. So the first thing is that, so the first node will go to the left subtree and the second node will go to the right subtree. So that is how it's the first step is like that. Now next thing is that we have to insert 8, right? So the next element is 8, we have to insert it. So obviously the next position is obviously this thing, this position, right? So if we add 8 over here, actually we have to add 8 over here, right? So Yeah, when we add 8 over here, what will happen is that it is a correspondence property violation. One violation will occur. That is a correspondence property violation. That is, if we add 8 over here, 8's corresponding element will be 5 because 8 is not having a corresponding element over here. So 8's corresponding element will be 5, and 8 is not less than or equal to 5 is false. So that will be a correspondence property violation. So we'll have to swap these elements. So 8 will come here and 5 will come here. I'll show you. Yeah. So this will be the result. Okay, so when we add 8, it will come like this. Actually, there is one step over here. I mean, we can, if you want, you can add it like you add 8 over here and then you just show it with an arrow mark. I'm just skipping that step and I'm just explaining and just adding the result, what will happen. Okay, so now we have added 8, so it will become like this. Now the next element that you have to add is 3, right? So when we add 3, so the next position is this, right? So if we add 3 over here, there is no violation because -1 is less than 3, mean heap property is satisfied, and the correspondence property is also satisfied because 3 is less than or equal to 8. So that is also satisfied. So we can add 3 over here. There is no violation. Yeah, so it will become like this. So the next element that we have to add is 25. So 25, the next position is of this, right? So we have to add 25 over here. So then there is a violation because if we add 25 over here, what will happen? There will be a max heap violation. So this right subtree should be always a what max heap, right? So 25 cannot come over here. So what will happen? We have to swap it. 25 we have to swap it with 8. So what will happen? Yeah, we swapped 25 with 8. See, 25 is swapped with 8. Now what is the next element? Is 30. So we have to add 13 over here. If we add 13 over here, that is fine, right? It's not violating any property. See, if we add 13, 25 is the highest element and 13 is its child. So maxi property is not violated, and now any correspondence property is also not violated. So that's fine. So we can add 13 over here. Yeah. So 13 is added, right? Now the next element is 15. So we have to add 15. The next position is what? This, right? It's a binary tree. See? So we have to add 15 over here. If we add 15 over here, let's check what will happen. The min heap property is not violated because it's, all the elements above are smaller than 15 only. But if we add 15 over here, what will happen is the correspondence property will be violated, right? So 15's corresponding element will be what? The corresponding element of its parent, that is 5. So 5's corresponding element is what? 8. So 15's corresponding element will become what? 8. So 8, so we have to, what will be? 15 is less than or equal to 8, which is false. So what we have to do is we have to swap 15 with 8, right? So that swapping, after that swapping, what will happen? Yeah, so we have swapped 15 with 8. So yeah, here is 8 is here and 15 comes over here. Now the next element that we have to add is 11. Okay, now adding 11. So the next position is here, right? So while adding 11, the min heap property we have to check because this is a left subtree. So the min heap property is not violated. The next property that we have to check is, correspondence property. If we add 11 over here, so 11, it does not have any corresponding element. So 11's corresponding element will be the corresponding element of its parent, that is 15. So 11's corresponding element will be 15 if we add. So it's okay. 11 is less than or equal to 15. So no min heap property is violated and no correspondence property is also violated. So what we can add 11 over here. Yeah. So we added 11 over there. The figures are a bit small. I hope you can see it clearly. Yeah. So we had 11 over there. The next element is 10. So we have, where should we add 10? This is the next position, right? So you have to add 10 over here. If we add 10 over here, min heap property will not be violated, right? So, and let's check the correspondence property. Correspondence property is also not violated. See, corresponding element of 10 will be what? The corresponding element of its parent. Corresponding element of parent is what? 13, right? So 3's corresponding element is 13 and 13 is what? And 10 is what? Less than 13. So correspondence property is also not violated. So we can add 10 over here. Yeah, so we added 10 over there. Now the next element is 19, right? So 19, where should we add 19? 19 should be added over. This is the next position, so 19 will be added here. So if we add 19 over here, obviously the min heap property does not seem to be violated. That's fine because 3 is less than 19, so that is fine. And so, but next thing that we have to check is the correspondence property. Correspondence property, see, 19 if we add over here, 19's corresponding number will be what? The corresponding element of its parent, right? So that will be 13. So 19's corresponding element will become 13, but that is not right because 19 is less than or equal to 13 is false. So what will happen? We have to swap 19 with 13. So after that swapping, what happens? Yeah, we have swapped 19 with 13. So that swapping take place. And now the last element is 9. So where should we add 9? This is the next position. So we have to add 9 over here. So if we add 9 over here, is any property violated? No, the max heap property is not violated because its parent is greater than 9. So max heap property is not violated. So we can add 9 by saying max heap property. But see, here the 9's corresponding element is what? 8. Yeah, 8 is 9's corresponding element. So corresponding element property is also not violated. So we can add 9 over there. Yeah, so that's how we got the result, right? So this is the deep that we got by inserting these elements accordingly. So yeah, this is the same elements. I've just jumbled it. So maybe if you try different order, maybe you'll get a slightly different deep. Like maybe you can just swap get those 3 and 5 swap. But however be it, you have to just make sure that the properties of the deep is satisfied. And this was a very simple example. Like there can be like conditions if the number of elements are large and some very much difference is there between elements or something, then there may be also a chance for not only when there is a large difference between the elements, but there may be a chance for like multiple violation in the same step. Like you have to do 2 min heap violation or max heap violation will be like multiple violations can occur. So accordingly you have to swap, and at each step you have to make sure that there is no violation and then follow. Like you can have this first, this will be violated and then you form a deep, and you see that again this is also violated, so you have to swap between that and that forms a deep. So similarly, like in min heap and max heap, both situations multiple violations can occur, so you have to see to that. Hope you understood this creation of a deep. Now this was a very simple example. Now I'll just add some more points to it. Suppose you think that instead of this -1 5, it was 5 and then -1. Then 5 will go to the left subtree and -1 will go to the right subtree. So that will be a corresponding property violation because 5's corresponding element will become -1. So 5 is less than or equal to -1 is a violation. So that there will be swapping in the first step itself. Now think that instead of adding, we added 15, right, to this node. We added 15 and there was a violation. So 15 was supposed to be added over here and there was a violation, corresponding property violation. So we swapped 8 with 15. So 15 came over here. Suppose if instead of 15 we were adding 28, then what would happen? We should add 28 over here. So obviously we'll swap it with 8 because corresponding property is violating. So 28 will come here and 8 will come here. instead of this 15, 28 comes here and 8 comes here, and again there is a max heap violation because 28 is larger than 25. So max heap violation is here. So one more exchange takes place. 25 comes down and 28 comes over here. So just one case like that. And just one more thing. Yeah, instead of adding this 11, after that, instead of adding 11, suppose we are adding minus 100. Okay, suppose if that is the case, then minus 100 will be anyways, the next node is this, so we'll add minus 100 over here, and since min heap property is violated, we'll swap it with 5. So 5 comes here, minus 100 goes here, and again min heap property is violated, so minus 100 goes here and minus 1 comes here. So that is just, I have just told some conditions because this was a very simple example. So these are the other conditions that can occur. Okay, now coming to the deletion of the minimum element and the maximum element. See in this figure, this is an example of a deap. This is a very small deap, only 5 elements are there. In this, yeah, it's a deap because this is a left subtree and it is a min heap, and this is a right subtree and that is a max heap. So which is the minimum element in this deap? That is minus 1, and the maximum element is 25, right? So the minimum element is present in the left node of the root. This is the root, and the left node is minimum element, and its right node is the maximum element, 25. Okay, now when we have to delete the minimum element, what we do is we just replace the minimum element with the last node. So which is the last node here? 8 is the last node. So we just replace the minimum element with the last node. That is minus 1 will delete and 8 will take its place. And there are certain procedures that we have to follow. And even if we have to delete the maximum element, the same first step is the same. That is, we have to delete the maximum element. We just replace it with the last node. Whichever is the last node, we will just replace it with the last node. That's the first step in both minimum element deletion and maximum element deletion. Now we will just see how minimum element deletion, what's the next step that we have to follow, and similarly in the maximum element deletion, what we have to follow, we'll see. Okay, now coming to the min element deletion. See here, the first step is saying that we just delete the minimum element and we'll just replace it with the last element. The next thing that we have to keep in mind, then when we replace it with the last element, the min heap will be disturbed. So we have to continuously check the min heap property is violated. If once it's violated, we have to exchange it, and we have to repeat it till the last when the property is not at all violated. Till then we have to repeat the checking. And the next thing is that once min heap property is satisfied completely, then you have to check for the correspondence property violation. That means we have to check whether the correspondence anywhere the correspondence property is violated, and if it is violated, then you have to do the necessary exchange. And if at all some exchange is taken place, then there may be a chance for a max heap violation also. So then we have to check the max heap violation. If at all, you have to check that, and if there is any violation, we have to do the exchange. Now similarly, we'll do the max element deletion. That is, we'll just delete the maximum element. First step, and first step is same. We'll just replace it with the last element, and then so you have to check the max heap first, whether any property of the max heap is violated. Then if it is violated, we have to do the exchanging, then recursively till the max heap property is satisfied completely. Then we have to check for the correspondence property, and if it is violated, we have to do the exchange. And then if at all we exchange some elements, there may be a chance for a min heap violation also. We have to check that, and then for min heap violation, once that is done, the deletion will be completed. Yeah, and both the deletion, that is min element deletion and max element deletion, both of it requires the order of log n time. Just keep it in mind. Okay, here I've just included an example of deleting a maximum element, and here I just summarize the steps. First you have to do is you have to replace the maximum element with the last node, then check max heap property, then check for correspondence property, then the min heap property. So we'll just see it in the example. So this is the same example that is in the figure 1. So we are deleting maximum element. So our maximum element will always be in where the right node will be the right node of the root. So if you have to delete the minimum element, it will always be in the left node of the root, as I've already told you. So here now we are going to delete the maximum element. So the maximum element is in the right node of the root, that is 25. So we're going to delete 25, and we're going to so how we do is that we just replace this 25 with what? The last node. 10 is the last node, so we just replace it with 10. So yeah, that's done. I've just replaced it with 10 now. So the next step is that we have to check for after replacing it with that, we have to check for max heap property. Okay, so we just check for max heap property. So that is violated, and that is 10 is 10 max heap. So maximum number element should be at the top, right? So 10 is less than 19. So there is a max heap violation. So we just swap it. So what happens? It will become like this, right? So now this is very small deep. So if it was more element was there down here, so we have to check when 10 comes here. We have to check with other elements also, and continuously do till the whole max heap is in order. Okay, and so now just our max heap contains only this much element, so that is done. Now we have to check for what? Correspondence property violation. Okay, so max heap we have just exchanged that, and now we are checking for correspondence property violation. See the correspondence property violation, we have to check for each element, and this is fine, and all this are fine, this is also fine, this is fine, all elements are fine. But see, yeah, 9's corresponding element is 3's corresponding element, which is 10, and 13's corresponding element also will be 3's corresponding element, which is 10. So see, yeah, 13 is less than or equal to 10 is a violation. So what you have to do, you have to just exchange it. All other corresponding property, it is satisfied. First node and all, it's satisfying. So there may be cases when some are not satisfying. So we have to do exchange from there and come. Okay. So now here only the last node is being violated. So we have to do just that exchange we have to do, right? So once we are done with that, it will become like this. So okay, now 10 comes here and 13 goes there. So now we have to check for min heap violation, but since it's a very small example, there is no min heap violation present over here. If it was there, then we have to exchange, like whichever element we have just added, from there only a min heap violation may occur. So we have to see that element and do the necessary exchange to how much ever level it may go. Suppose if this element was minus 5 that we have added over here, then it would be a min heap violation. So we have to exchange it with this 3, and again it will be a min heap violation. We have to again exchange with that. So 3 will come here, and minus 1 will come here, and minus 5 will come here. So that is how we do a maximum element deletion. And similarly, we can do a minimum element deletion. For that you have to replace the minimum element with the last node, then you have to check min heap property, then correspondence property, and then max heap property. So that's about deleting element. Just one last point. It's a silly thing. Those who know min heap and max heap deletion might be knowing this. That here we are exchanging 10 with 19. We could have exchanged 10 with 15 because 10 is less than both 15 and 19, right? So, but if we exchange it with 15, what will happen is it again creates a max heap violation. So, in order to avoid confusion, you have to always exchange this element with the maximum element over here in case of a max heap. If it was a min heap, then what it will be is that if it was 12 here, then we have to exchange it with 8. That is the minimum element among this. It's just that, and you have to keep this point in mind while doing insertion also if some exchanges are being made. Now that was the last slide. Thank you.